We will now be looking at immersion microscopy. So we may be familiar with the concept of immersion microscopy for light microscopy, where we can immerse the space between our objective lens and the sample with a medium that has a higher refractive index than air. For instance, water or an immersion oil with a refractive index of, say, 1.5. The purpose of this immersion medium is to mitigate scattering of the light at the interfaces and increase the excitation light cone and the detection light cone, and thus our resolution. Now, in electron microscopy we can also use immersion modes. So remember that the equivalent of the refractive index in light microscopy in electron microscopy is the voltage of the electrons. So an immersion medium in electron microscopy can be an electrostatic field. So because an electrostatic field can change the acceleration of the electrons, and thus the speed thus be equivalent to the refractive index for light microscopy. So electrostatic immersion is one example of an immersion field. Magnetic immersion can also occur. We will get to that later, but first we will focus on electrostatic immersion. So remember that if we have the primary beam hitting the sample, we generate secondary electrons and we generate backscatter electrons, typically the secondaries with an electron energy lower than 50 electron volt, most of them in between 0 and 10. Backscatter electrons have an energy close to the primary beam energy. So now in electrostatic immersion we apply a bias field, a retarding field for the primary electrons between the final objective lens, so the pole piece, and the sample. And you see that indicated here in the lower figure. Now there's an important thing to realize, where in the upper case, if we don't have an electrostatic immersion, we want to look at the sample with an energy of, say, 2 kilo electron volt. The electrons exiting from the objective lens have an energy of 2 kilo electron volt. That's the primary beam energy, and it's equivalent to the energy with which the electrons land and interact with the sample, land on the sample, the landing energy. Now in the case of electrostatic immersion, electrostatic field, this is different because the electrons are still decelerated when they exit the pole piece and are on their way to the sample. So in this case, if we want to have a 2 kV landing energy and we have a 1 kV retarding field, the electrons should exit the objective lens with an energy of 3 kV, they are further decelerated and then interact with the sample with 2 kV. There is an important advantage, and we will see that there's an advantage on the detection of electrons. There's also an important advantage from the electron optics perspective, because this means that in the microscope column the electrons can travel at higher energy, which is beneficial for mitigating Coulomb interactions that occur in the electron microscopy column. So this final stage deceleration can actually be beneficial also for the properties of the electron microscope. Also, we can think of chromatic aberrations, which are dependent on the primary beam energy. So the chromatic aberrations induced by the lenses in the microscope may also be slightly reduced when we travel with higher energy inside the column. Now here we look at what is going to happen with the electrons that are ejected from the sample, the secondaries and the backscatter. They will also feel this field and they will be accelerated by this field. They will be accelerated towards the objective lens. Now here you see the result of a very simple ray tracing simulation, initially for a situation where we have no bias applied. Note that electrons emitted from the sample, the secondaries, they follow a typical cosine rule. The backscatters is dependent on the angular spread induced by the atoms in the material and their atomic number. And so in this simple simulation, we just took certain angles for electrons that are traveling, 5 eV in orange, 1 kV in blue, so one typical secondary electron energy, one typical backscatter electron energy, and we just have them exit the sample under equidistant angles. So you see in this example, electrons are emitted, some close to the optical axis. They go inside the electron microscopy column. Then we have a few electrons that are hitting the detector. Note that in this case, without a field, the 5 eV electrons and the 1 kV electrons follow the same trajectory. So some hit the detector, and then there's electrons which exit the sample under such a large angle that they miss the backscatter detector. And so on the left, you see a cross-section of a segmented detector, and then in orange, you see the positions of emitted electrons in the detector plane. So you see the ones that fall on either of the concentric rings, they're actually being detected, but you also see electrons outside of this cone. And in blue, you see the positions of the backscatter electrons, so the electrons with 1 keV energy in this case. So also there you see some hit the different rings, and some miss the detector. Now we are going to look at the situation where we apply a 1 keV bias. So now a 1 keV bias in between the objective lens, so the detector position, and the sample accelerates the electrons. Of course, the low energy electrons, the 5 eV electrons, they will be accelerated a lot. So the 1 keV forward direction will contribute significantly to the 5 eV maximum 5 eV sidewards energy. So you see this in this image. Most of the secondary electrons actually go very close to the column and completely miss the detector. You also see that in the cross-section view, all secondary electrons passing through the position plane of the backscatter detector go through the hole in the center. Now interestingly, for the backscatters, we see also their trajectory curve, but it curves less because the impact of the field is less compared to the sidewards energy that these electrons may have, but they are still bended towards the detector. So there's some lensing which increases the collection efficiency of the backscatter electrons. You can also see this in the cross-section view, and there's less electrons missing the detector than there are in the upper image. And so we see that this electrostatic immersion field accelerates the electrons, focuses the electrons better onto the sample, and it removes all secondaries from the detection event. So it reduces a little bit of noise. Now there's an even more pronounced effect on the detector by this electrostatic immersion field. So not only do the electrons, the backscatter electrons, get focused a bit better onto the detector, they also hit the detector with a higher energy. So now if we look at this situation with 1 keV backscatter electron, in the upper situation, the electrons hit the detector with 1 keV energy. So that generates a certain amount of signal. Now in the lower situation, the electrons exit the sample with 1 keV energy, but they hit the detector with 2 keV energy, because they have also been accelerated with an additional 1 kilovolt. So this 2 kiloelectron volt energy can generate more signal inside the detector. So actually, not only is our noise level reduced, also our signal level may be enhanced. So we can actually measure this. So here you see the result of a measurement on a biological sample. You may recognize cell nuclei in this image. In the upper example, you see a situation without immersion field with a specific dwell time recorded. The boxed area is what is magnified under D in the image below. And so you can see this image is quite noisy. The lower situation has the same dwell time, but now with 1 keV stage bias applied, and we detect much more signal from the sample. The signal to noise ratio is obviously better, and clearly in the magnified view you can easily observe this. And we can see the cristae in the mitochondria, for instance, in the lower right corner of the panel F. So like I already said, besides electrostatic immersion, we can also have magnetic immersion. Actually, magnetic immersion occurs a lot, both in scanning electron microscopy, but typically in transmission electron microscopy. The sample is positioned in the objective lens of a transmission electron microscope, so it is in a magnetic immersion field. Now, if we recall from electrodynamics, so the Lorentz force acting on an electron actually leads to a spiraling path, which is also what we see happening here. So the upper image here is a situation, again, with electrons exiting the sample, in this case without electrostatic immersion, but with a magnetic immersion. And we see both for the secondaries and the electrons that they start to they start to swirl and they start to oscillate around the optical axis. Specifically for the secondary electrons, where the energy is low, we make a lot of windings towards the optical axis and back out when they go up into the sample. You can also see that where we have the position of the backscatter detector, the immersion field in this simulation stops, and there the electrons again go in straight lines. So also we see the backscatters are deflected, and in this case with a quite high working distance, this means that several of the backscatters are actually reverted back and may hit again the sample. So you also see this in the cross section. The secondary electrons now don't hit the detector anymore. They're actually even more narrowly focused to the optical axis than in the case of only the electrostatic immersion field, but also not so many backscatters hit the detector anymore. This is a situation that is specific for this situation here with a quite high working distance. And note that in practice, if we work with magnetic immersion, the working distance in an SEM is on the order of 2 millimeters. It's relatively small to prevent this effect, and then actually we can enhance the collection efficiency of electrons on a detector. Now in the lower situations you see the combined effect of the electrostatic immersion with the magnetic field immersion, and now you see the secondaries again are accelerated, so they don't circle towards the optical axis that much anymore, and they make 1 or 2 orbits towards the axis and then they go into the column. And also for the backscatters, now we see that more backscatters actually hit the detector and less are deflected downward. And so I think this is a nice illustration of how the electromagnetic forces, the Coulomb force and the Lorentz force, also act on moving electrons. Now these immersion fields are also important for detection, so they can enhance the collection efficiency, but it also means that a lot of electrons may actually travel close to the optical axis, so close to the primary beam axis. Note, however, that their energies may be different in different parts of the column, because they originate from the sample with a specific energy that's different from the primary beam energy. So this also means that in an electron microscope column there may be a lot of detectors inside the column. These we call in-column detectors. So a typical example is what we call a through lens detector, which is typically a secondary electron detector, which at a specific point in the column deflects the secondary electrons towards the detector. And as we have just seen in the images, that a lot of secondaries can be collected in a narrow cone along the optical axis, the collection efficiency for secondary electrons with a through lens detector may be quite high. However, it may also depend a lot on factors like the working distance, the strength of the immersion, whether we use magnetic and/or electrostatic immersion. Also, backscatter electron detectors may be located higher up in the column, typically by a detector that is called an in-column detector.